Nice. What is our
How you doing this fine evening, Daniel?
man, I'm doing $1 million. I'm just beyond ecstatic. This is just such a fine evening here on the east coast of Australia. And boy, do I have some cool stuff to show this group of people. I hope. How many people? We have 67. And so what are we considering uh our threshold for when we think we should go ahead, Lucas?
I feel like we're probably pretty good here. We got roughly half our cohort, so that's
Yeah,
pretty
I'm
good.
I'm seeing some old names in here too. I'm also seeing some friendly faces, people that I've taught before, both through Rectoff and not through Rectoff. Maybe that's one thing that we should say to the class. Um, we've decided that it would be a nice thing to allow previous students through Rectoff to join into the lectures, because there's a lot of content that we get through, and maybe the first pass at it isn't sufficient to fully understand it. We don't really see that it has any negative effect if there's more people around paying attention, and just makes a bit more of a tighter community, and might mean that people understand the material a bit better. So there's some Rectoff alumni in the group too.
Yeah, Daniel, I think you're good to jump in whenever you're cozy.
All right, sweet. Let's do it. Hello, everybody. Welcome to Rectoff Round 3 Full Throttle Edition. This time we're gonna hit that gas so hard, and we're gonna, I don't know, we'll do a little bit about learning about computer science, and a lot about learning about love and community and all that good stuff. Today kicks off Module 1, the Rust cohort. We're going to be doing our deep diving of Rust, and perhaps some motivation for why might we be interested in talking about Rust. Well, here's the pre-read that I'm going to go through. So screen sharing is working. But before we get to that, let's go GitHub Anza. So Anza is the premier dev shop for the Solana ecosystem. They make the famous Agave validator. They also are responsible for the SDK. And let's just have a bit of a scroll through the most active libraries that are here. We've got Rust. This is a pretty big one. This is a pretty big one. Like this Agave validator, this is a massive amount of code. Or Rust. Well, I guess mostly Rust. We got Pinocchio's Rust, the SDK is Rust. Don't know what that is, but it's Rust. SBPF is Rust. MCP, so what's this? That's the multiple leader proposal, I think. Mollusk, the testing, that's written in Rust. If we keep going, we're going to see a lot of Rust on this board. So talking about Rust generally, it will offer you guys the ability to understand, like theoretically, you would be able to look at production grade Rust, which I promise you that things like Alpenglow and things like Agave, these are most certainly production grade Rust. The devs who are building this stuff are, top tier Rust devs doing pretty incredible work. And but the thing is, to be able to understand what they're doing, you don't need to, go through the same things that they did and be as good a dev. You can understand their code and interact with their code just by getting at least down into the details well enough that all of this stuff is at least somewhat familiar to you. So the smart contracts that are written for the Solana ecosystem are Rust, but also a lot of the entire ecosystem aside from that is Rust. And it would be good for you to be both able to interact with the smart contracts directly, also able to work with the external ecosystem, and potentially to be able to find bugs in that stuff, because I promise you that there's bug bounties for a lot of those things, like all around. Furthermore, I think that there ends up being audit competitions for stuff like, Lucas, correct me if I'm wrong, but at the end of Rector cohort 1, there was it an ANZA or a Solana Foundation audit competition that went live? But I mean, there's different things around, like through all these ecosystems that not through these ecosystems, through the infrastructure there that you can be able to attach to. So learning Rust is a good step for learning how Solana, or the foundation for Solana. So I'm going to go through this lecture 1 pre-read today. It's rather big. We got a bit to get through. I then also have some extra stuff that would be awesome to go through. However, there is always opportunity for people to ask questions. Feel free to type questions in the chat. I will try my best to get to them. You're also welcome to raise your hand, to unmute your microphone and talk to me. I very much prefer doing live coding examples and actually working through the ideas that you have, because you will have better ideas of what is confusing to you than I will be able to guess for what is confusing to you. And if you have some idea like, well, what if this was like this? How would it work? Let's write a program and let's actually just discover how it works together. That, of course, uses time. And so, as I mentioned in the town hall, I tend to go over time. So expect that we will probably take longer than the allocated time, but I'll try my best still to stay on track. We can always, if we're getting too long, we can roll some content into the office hours. Now, there might be mistakes in this. When people find mistakes, like, just say something in the Slack, generally, if you're like, I feel like this is potentially wrong, whatever. If you find a correction, I'll try and correct. Usually I try to batch things together because I don't want to like push and redeploy. If it's things like the visualizer down here, if it's in this is actually really easy to change. So if you say something here, like if I miss something, I can just quickly go and change that. Cool. Sweet. So first of all, I will do a bit of context. So what is Rust? Rust, as you know, is the programming language which is used mostly for the Solana ecosystem. Why did they want to choose that one? It's a systems level programming language, meaning that we have question? Maybe not. If you do, feel free to go ahead, but otherwise I'm going to just do a little bit of context building first. So this programming language, being a systems level programming language, means that we're afforded control over our memory. We are able to go to the memory of our program and say we want to allocate some here, so add some here, do things like this. This is in contrast to a language that maybe like Java or something that does not give us control of the memory ourselves. Instead, it says you can't be trusted to do that properly. You're going to screw something up, so I'm going to handle that for you. The danger when you are given the power to control your own memory is you will also given the power to screw up your own memory. You can create memory bugs and you can create vulnerabilities in your code by nature of having memory bugs. And if you have a look online, like how many vulnerabilities, like I think you can go Google, like look up Google 0 Day, and they have like a spreadsheet across the years for what kind of vulnerabilities that they saw in their ecosystem. And I think a third of them or 40% of them are memory bugs. And of those, there's like even one particular memory bug which takes up a third of those bugs, or 50% of those bugs. So Rust promises that it's going to allow us to control our low-level memory, but it's also going to prevent us from, even more. So almost 70%. That's even more than I was expecting. Rust promises that it's not only going to allow us to have control of our low-level memory, but as long as we work within safe Rust, there is a unsafe keyword, but as long as we work within safe Rust, it says you're not going to be able to compile code that gives you that memory error. And what I mean by that is, at the stage where we've written our source code of our program, if that source code has the possibility of creating a memory bug, when we try to compile that down to a binary that we then might run on our architecture, the compilation phase will stop. It's not that we get a binary that we then can run, and if it's going to do a memory error, it will panic. It's promising us that it won't even give us a binary if we're allowed to do that. And so it's got a pretty big claim that it's going to protect us. These guarantees of memory safety work independent of the target. So whether you're compiling for your smart contracts, whether you're compiling like on Solana in SBPF, or whether you're compiling to WASM, ARM, x86, it is an analysis partway through of the core language, which allows us to have these guarantees of memory safety. So that is why people choose Rust. So I'm going to try and make you understand what are those guarantees in particular. I'm going to get really into the details of what ownership is in the second week. First, in order to understand what we're promised and what we're afforded by having memory safety, and what we are opting out of when we choose to use the unsafe keyword, which you will find plenty of use in the Solana ecosystem of people using the unsafe keyword. I plan to first give you what even is memory on a running process. And so that's what our first and that is a really, really big topic. I only provide a lens of it. And I promise you that what I have here for you is a simplification, and that there is more to the story. But we got to draw the line in the sand somewhere. We can't have it all at once. I will take this opportunity to read a couple of questions, and then I'll get even deeper into it. Looking for bounties. Yeah. My question is, Rust stack memory works very similar to EVM's stack operations, and the heap memory and operation is also similar to EVM memory operation. That is, they are the same types of data structures. You can think of it, or sorry, I shouldn't say data structures. The heap is not a data structure. The heap is a region of memory. That is a fair way of thinking about it. However, the purpose of the EVM stack is it is a stack that stores opcodes. And so the actual bytecode, which is processing, is doing pushes and pops of the stack operations. In this sense, we're going to see here the same type of data structure. So it's last in, first out, but it's going to be used as a call stack. So instead of processing the data as the instructions do it in this way like this, we're going to see as we scope into calls, this stack is going to chunk down, and this is going to be at like a higher level. Get into the details of that, but they're similar but not the same is my answer to that question. It looks like Amal has an answer. I could be wrong, but the EVM has different memory abstractions: call data, try-base memory, and stack. Basically, you don't create memory in EVM, whereas in other environments where you create and manage heap memory is a good abstraction. I would trust Amal on that, because he's going to know more about the EVM environment than I am. It's been a long time for me. But in the sense that we have some other region of memory, definitely the heap is running on architecture here, as I don't think the same, but there is some other region of memory that I think Amal captures well there. So if we don't use unsafe Rust, the chances of memory bugs are negligible since the program won't compile. If you don't use unsafe Rust, the chances of memory bugs are, yeah, negligible to the point where like they should be zero, like, you know, asterisk TM, you know, watch the Rust Zulip to see if someone's found one. But pretty much, yeah, they shouldn't be around. We have protection and unsafe as well. From memory bugs, percent related to memory bugs. We do have some ability to protect ourselves in the unsafe world as well. If we know that we're preventing ourselves from having something called undefined behavior, I'll talk all about this later. We know that we're not going to have, or at least we have some ability to be able to analyze that, and then we should feel confident that we aren't having memory bugs in that setting too. Okay, cool. So this is a massive document. First, I talk about virtual memory and paging. This is going to tie to, just to give you a bit of what's coming up, this is going to tie what is memory on architecture and how does like our CPU's kernel actually decide that it's going to allow us access to RAM. When it has allocated some memory to us, what is going to be the memory that's allocated to our process, and how do we like to think about that layout, or what's the view that it gives us? Within there, we have stack, heap, and static memory. These are three main regions of memory that exist within that layout, and they all serve a purpose trying to address a different problem. And then it looks like I got some extra reading and resources that I put down there for you. So let's get cooking. The first thing to understand is what I'm trying to capture in this diagram. And so I'm going to do an overview of this stuff, but I encourage you to spend some more time reading through it and just use my explanation to help understand it. But I'm not going to like read it out verbatim. I'm going to talk about the ideas and encourage you to have some discussion about it. So what I'm trying to explain in this paragraph in this diagram is there is actually, when we talk about memory, there is RAM in our machine, and there are a bunch of pins, and they can have a state. There's some sort of state in there, like 1 or 0, where we're storing the bits of information. Now, it would be pretty wild if they would allow us to just directly go into that, and for everyone and every user program that we can think of in an unpermissioned way to just have direct access to our RAM pins. We find that is not a great way to design computers. That instead what we want to have is the operating system's kernel have a buffer between us and doing that, or not a literal buffer, but that there's some sort of permission system that is not allowing us to access that directly. And instead, we talk to something called the MMU, or the memory management unit, or at least the process that we create, the program that we're trying to run. It wants to talk to the memory management unit. And what we have and what the memory management unit is going to provide us is a virtual address space. So there are literal addresses that are our actual RAM memory addresses, and we don't even get to see those. It doesn't let us have a look at them. It says, nope, you're not allowed. What it says instead is you can look at these virtual fake memory addresses, and I promise that I'm going to do all of the hard work of actually making sure that this connects to the physical architecture in a coherent way. And the way that it provides us this virtual address space is in pages. So there's like, think of it as like you have a page with your addresses and where you can store your data, and you have multiple pages, and it will load those pages into your virtual address space when you request. And so a Rust process and when I say the word process, what I mean is a Rust program is the source code that I write in Rust. When it becomes a Rust process is I've compiled that down into a binary, and now I've decided to execute it, which means that my CPU and my computer has in some way decided, okay, cool, we're going to go grab that binary load the information in, and we're going to provide some amount of memory that this program is allowed to interact with. And we're going to start going through the instructions, and it, manipulates the state, it manipulates the memory, and the CPU executes everything until finality, assuming that the program does indeed terminate. So a Rust process, how is that going to interact with this virtual address space? We get it via this, via the pages. So here I'm saying, like, just imagine that for now, your Rust program is going to fit inside one of these pages. That's all that the operating system allows you to look at, is your fake page of addresses that aren't real addresses. And then behind the scenes, this thing is going to connect that to the actual physical architecture. So when we're loading a Rust process into one of these pages, what is the view of memory that we get? And remember that all of this is designed by programmers, which, like, I guess similar to all of us in this room. So we have we can make the computers, we'll code them to do whatever it is that we need to do, and we try to do it in the best way. And the way that we've kind of agreed upon that we like to think about memory is as a contiguous block. We, of course, can write an operating system memory management unit that doesn't show us pages like this, but this is one way that we like to think about it. And so what we think of is there's a high address and a low address, and inside that address space, we think we have the allocated memory for our Rust program. There are key segments inside this address space, and the addresses that are provided to us, as I said, they're not going to be real. And if we have a look at what's provided, we might notice something. Like if we have a program, generally the high address is going to be something like, OXFFFF for ages, and you can consider a low address like this, so like as hexadecimal. If you were to actually look, when you're provided these fake addresses, at how much memory on your RAM this would take up if you actually tried to utilize all this space, you would quickly realize that this is just impossible, that this is going to far exceed the boundaries of what your computer can actually hold. So our computer it lies to us, and it tells us you've got all of this space in your RAM, more than you actually bought, and feel free to utilize it. But remember that it's really all just connecting down into here, and it's an abstraction to help us reason about what our program is going to do. So inside this massive address space that is provided to us as a contiguous block, we have when we're executing it, so when we decide to start running the program, we decide to start executing it, we are taking a compiled binary, and that binary has all of the information that came from turning the source program into the actual into the binary that's going to be run. So whatever information that is actually needed. Of course, in that program, there's going to be the actual instructions, bytecode instructions. So did you have a question there, David? Or maybe not? Someone else? I think he's yeah, I don't think he's talking to me. Cool. So David, if you could mute yourself. Okay, legend. So the actual instructions, like the bytecode instructions, we need those in order to know, like, what is the logic of our program going to do, and so we can step through our program. We're going to store those, we can think of down in the low address space. And so this is our compiled binary, and we want to store it in memory in a read-only format. Like, we don't want someone to be able to write other instructions into our compiled program, because then we can think of some tricky ways to inject in them some instructions which are going to end up creating a vulnerability and exploiting our program. We like to think that above the text segment or code segment, we have our static variables and string literals. And so this is populated at the start of when the program is executing. So we're taking the binary in, we take our instructions, we put them in the text segment, and then we go, okay, what other data is needed? We can think that when we run a program, there's things like error messages, which are strings like we panicked, here's where I panicked, or overflow detected if we're compiling in particular ways. Those need to be stored somewhere in order for the program to be able to call upon them. They get stored in the data segment. So we have a read-only data segment, but we also have a mutable data segment. The block started by symbol is also populated when we're first loading in the program. And this is, if you're in C, I believe this is storing actual uninitialized information. In Rust, I believe this is storing just zero initialized data structures. It's not really, I'm putting it here for completeness, but I wouldn't really worry about this so much. It's probably enough to just remember our instructions are in the code segment. Other things like string literals for error messages or specifically declared static variables, they're going in the data section. If we were every time that we bring a program into memory to be able to execute it in a process, we also store some other environment information, environment variables, how many arguments were provided to the running instruction, which is argc, and then those actual, when I said instruction, I mean program. So how many arguments were provided, what are those arguments as a vector? And so we store the program data up the top. And then what's remaining is, this is all free space when we start the program. It's there in the address space, but it's empty, we can think of it at that stage. Nothing has been written there by our program. But as our program runs, this is the space that it's going to utilize. So I'll show the use of the stack, but the stack is used for function calls and their data. And so with a Rust program, the first thing that happens whenever we start a Rust program is we call the main function. And the main function is, so then this is how we kick off after we've loaded everything. We're going to orient to the start, the initial function, generally called main, and we're going to start executing from there. And this is going to manipulate some data. And so we add a stack frame on here to be able to work with that. The heap is an area where we're going to be able to work with data that might not be sized. This is a deterministic, it's like an algorithmic way of adding information. We're going to go last in, first out on function calls. I'll show you this all in more. I'm just covering broadly first. But this is more so for storing groups of data in an unstructured way. So we have box, new, vector. So these are saying, I want to put some data out there, not storing it on the stack. I might want it to persist in other ways. I need a zone to be able to pull that. So we just dump it on the heap. That's where it goes. Now, something that I have written here that I just read, this heap grows up. It isn't that the heap grows up. The stack does grow down. This part is right. But the heap is more so, it's going to talk to this memory management unit through some, API, I guess you could think of it, or some interface that Rust is providing us. And it's going to figure out where is it going to put some space on RAM. Of course, it's not going to actually show us that. Instead, it's going to show us with virtual pages, and it's going to show us inside this region of memory. Here is where you're allowed to put your data inside the heap. So all of that is an overview, and I don't expect that will make a lot of sense just yet. But if I do the overview first, and then I go into the actual details here, it hopefully will make a bit more sense. So that should orient us for where we're going. Let me just have a quick look to see if there's any more questions. Why do we even have to use unsafe Rust? When you get to any level of Rust that is beyond, small projects, anything at scale, you will begin to find that the restrictions on the borrow checker might be costing you performance. You might find that their way of restricting you is too restrictive. You might know for a fact this program is safe, it cannot have a memory error, but the rules of the compiler, in order to stop you having memory errors, they err on the side of caution. They're an over approximation of what's needed. So they stop some safe programs as well, so that they hope to never allow an unsafe program, because it isn't easy to just perfectly iron out what the exact rules are that the compiler can allow and disallow. So in that approximation, there's a gap that means safe things are also disallowed, but it keeps getting better with time because compiler researchers keep figuring out more and more ways to actually narrow that gap. Reasons why you might want to do that are things like what is Nariman, always correct me if I get your name wrong, mentioned there, things like zero copy, working with raw pointers directly, things like that. Michael or Michelle, do you have a question?
It's Michael. I just had a question regarding like how it decides to use pages for your Rust program. So like in terms of like multi-threading, how does a page split that, or does it use multiple pages for different threads?
So what's going to happen is you can think of if you go into, so the difference between multi-process and multi-threading is a thread is going to be contained inside this process. So what we can think of is there's a bunch of space allocated here for a stack. When we say, I want to split this into two threads, what we're asking it is, instead of just considering this is your stack, take the history of it and split into two stacks and interleave the instructions on one particular processor, or however your CPU is going to work it, but it is only inside this address space that it is working. And so both processors will have access to this same, both threads will have access to this same heap, but they will not have access to the same stack as they go on in future. They will be able to see things from the past together. And if you're working with Rust, there should be a restriction on what they can do with that stuff from the past in order to be memory safe. Other languages will not necessarily do that.
Okay, so that's really clear. So when we are like technically moving ownership from, let's say, one thread to another, for example, there would be an actual move happening from one part of the stack to the other part of the stack, right? Like where that split happens.
Yeah, correct. There will actually be distinct regions of memories that are permissioned in different ways that's happening. And when you do a move, and I'll show you clearer in the next lesson, when we're actually doing a move, there's the move as we think of as permissions around ownership. And then there's what's actually still there in memory that we can go and witness. And these things don't line up, but as in the data is still going to be there, but there will be actually a transfer of permissions if you think about it, but there will be two separate regions of memory for both stacks.
Okay, thanks.
Excellent question. Love Gupta, do you have a question?
Yeah, hi. Am I audible?
Yeah, you're audible.
Yeah. So my question is, let's say we are using zero copy, right? So what would be the architecture of that? Like we'll bypass, right? Like, sorry, we will like give the access of kernel memory, right? So if that program is compiled and converted to binary, so the architecture would be same, right? Or is it different?
Maybe something that the architecture is going to be the same. It's going to be the rules around how we access the data are going to change. I do want to disambiguate something. When we say zero copy implies that we need to use a raw pointer, we could actually still do zero copy using borrows inside Rust. However, for sufficiently complex code, you might find that you need to step away from borrows and you want to use raw pointers. An example of when this happened is Pinocchio. Also, by stepping into the raw pointer world, you are able to make things more performant, but you have the obligation to make sure that you aren't introducing bugs when you decide you want to do this.
Okay, so like what I was thinking, like let's say there is a heap, right? It
Mhm.
will give us a pointer. So I was
Mhm.
thinking there is an unallocated space will be skipped and that stack will be skipped. And from that heap area, we will give that pointer to that kernel stack where the memory is present to the user into the user space, I guess.
Yeah, when we're doing let's maybe, I love your question. I think maybe what we should do next is
Okay.
make sure that everyone understands the stack and heap and
Yeah.
we're all on the same page. But feel free, especially if I forget, feel free to tell me that you want to discuss this again before we go. Nice. Okay, that looks like something else. Default stack size for Rust would be 2 megabytes. That's determined by it is determined by your operating system. I am not even sure. I haven't had to look at that anytime recently, so I'm not even going to make a conjecture. Why do we need to understand the memory layout? So by nature of using Rust, you are going to have exposed in what's going on with the memory. I see your question, by the way, Amal. I'm going to get there. I might just read through these ones first. But you are going to have the underlying nature of the architecture exposed to you by memory errors. Rust has tried really, really hard to make their memory errors able to be understood and helpful for people who aren't really understanding what the architecture is underneath. But at the end of the day, it is misusing these sections that is what the ownership rules stop you from doing. And so when you are breaking them, there is going to be some relationship between information that is on here that you are going to need to correct the behavior of. And it isn't that one way that you could decide to be a developer is to go, I don't need to learn that. I'm going to go and just make the LLM do it, and I'll never learn how to do it. But that's generally not a good way to approach anything that has the word engineering with it. So software engineering and development, you will always limit yourself if you're not prepared to actually understand how things work. The virtual address space and page side is decided by the operating system too. Yeah, absolutely. All of this is decided by the operating system. Shagun, I think I said your name right. How do these topics help in auditing? Yeah, the mental model of what's going on can only benefit you as you decide that you want to step and work with these systems. Whether that will be because you will be faster, because as you're reading code, you will have internalized what is going on in the system, and so you'll understand what things are saying easier instead of being confused and trying to figure out what is going on or how did that work. If you at least understand like at the end of the day, when you're auditing something on a computer. Understanding how computers work, it's not going to hold you back. It's not going to hurt you. It's going to help. Memory layout is the backbone of security. On God, man, I love that. Correct. There are some people that would argue that understanding how this stuff works is the key to just being able to find where there's. If you understand memory layout and you understand permission systems and information flow like security, then you should be good to look at any system pretty much. I don't actually subscribe to that belief, but some people do subscribe to that. Because memory layouts in the foundation, also the language, maybe getting mental model, love it. Also, welcome back, Misak. Can someone link to the docs, dive deeper into the memory stuff in Rust? Yeah, just look up Rust docs, Rust learn. Definitely most things come sibling out of the OS. Yep. Amal, it's your time. Yep. I knew that this would happen, but yeah, ask your question.
It has to do with the well, now that you've talked a bunch of things, I want to make a couple of observations.
Yeah.
I'll start with the latter first. For me, like as I'm learning Rust, the language of understanding the system is through the borrow checker, which are a set of rules. But those are just rules that enforce like temporal state of what's happening in memory. And when I have to debug a program, or I force myself to debug it, the machine itself doesn't know anything about borrowing. So knowing how to project the borrow checker's restrictions on or rules on the memory, it's really helpful to understand what's happening at runtime or what's happening at a level that'll cause a panic. So that's my observation about why it's beneficial to learn this. Your mileage may vary. But to the first part of my question is thread safety. It's been a while since I did real systems programming, but I remember there's like TLS, thread local storage.
Yeah.
And I would assume that the same rules the borrow checker will apply to that region of memory per thread, and then enforce that. Actually, I don't know how it happens. Like, so there would have to be global.
You will
and
need to
thread
opt
local.
into thread local storage though.
What do you mean by that?
There's a macro in particular to say I want this to be thread local. Of like the stack, when you create another thread, you'll get like separate stacks, and these will be thread local. And then you are specifically able with a macro, I believe, able to take like another region of memory, like the heap or something. Oh, I'm getting risky. I can show you a place where this is happening in production code, but there is specifically like you have a thread local macro to say I want this to be thread locally stored, which is part of the core compiler.
Oh, that's awesome. I have to try that out. Thanks,
Yeah.
Daniel.
Yeah, no worries. And I see there was where did I see it? I saw someone talking about Tom. Awesome. So all memory, this is within a Solana virtual machine where the heap is shared. Really, because what we're going to see is this set of rules is then broken again, and there's a whole other set of rules that work when we get to the SBPF runtime. However, the SBPF runtime and all of the rules that it is going to have for the heap and its stack and every single thing that it's going to store, all of those are stored inside a validator's heap. So we're starting right now just from the bare bones. Let's understand what stack, heap, and these are just on a generalized operating system. And then we can think, okay, well then if we're a generalized operating system is what's going to run a Solana validator. And then inside the Solana validator, we're going to execute another VM that has its own rules. Nice. Cool. So let's get into talking a bit deeper about stack memory. So I refer to stack memory as like the call stack. It's also called this by other people, and that's because what we're going to put on here are call frames. A frame is we're going to get one frame per function call. I'm going to show all this in more detail. Inside the frame, when we call a function, if we think of a function signature like something like function main, or let's choose something else, function other, and then it might have an A, which is an I32, and maybe it returns an I32. So this function, it has, we want to reserve space for the arguments here. So that's these arguments here. Inside the body here, we might have some, we're going to have some statements, like maybe we're going to say, let X equal, something, I don't know. But these are all local variables to the function other. So we need to reserve some space there. And then this is actually very hand wavy, but for the system that we're going to consider that we also reserve space in memory for the return value. that actually could be inside a register and is far more likely to be inside, if not certain to be inside a register on your CPU. But for the system, for the way that we're going to reason about things, we're going to consider that a call frame for one function is going to reserve space for all of these things. And I would, so here, let's just jump into the visualizer. So I think that just like how I tried to explain that stuff right then, this stuff is really hard to express just verbally or by looking at a static program like this. So what I did is I made this website for you, and I hope Ayomide, I wonder if you might be, yeah, legend. So with this visualizer, what I'm hoping to show you is that stack that I just described before. I want to make this a bit more concrete by letting you guys step through, and the arrow keys work, so you don't have to click on this, but I want you to be able to step through a Rust program at the source level statically and get some connection for what am I trying to express by what I've described for this stack. And I wrote a little description here to try and also, like, in case you're like, okay, what exactly am I looking at? Here's a little description to go with it. I also thought that it would be nicer for you guys if I diffed out what was different in red, so you can see what changed and what's the same from when we stepped through it. So without more chat, let's actually get into the nuts and bolts of this. So here we have is that big enough, by the way? Can you guys see this? Maybe I'll just bump up one more, because I mean, you say it's okay, but maybe this is better. So here we have the main function, which we're used to being the start function for our Rust program. And we see that we have a statement inside there, which is assigning the value of 5 to the variable x. And we see that we then are storing to result the result of another function call. So remember what I said, we're going to do different call frames for different function calls. And this function is defined here, and it takes in some argument. It does an addition to it, and it stores that value in y, and then it returns 3 times that value. So let's step through this program, like line by line or statement by statement, and let's have a look at how we manipulate the stack. So the first thing to mention is the stack is always at the high level or the high address space, and the way that, and obviously everything's different on different architectures and things are generally true. You can have differences on different architectures. These are just some customs that we have. So the high address space, when we first load our program in, so let's pretend that there's static data that has our instructions somewhere. We're just going to worry about the stack right now, so we're not thinking about that. The stack, it's empty. There's nothing there. It's unallocated. When we first get inside and we get to this point where we go, okay, we've decided that we want to execute the main function, this is when we allocate enough space for our entire function. And we can tell this before we've even gone inside it, because we're able to statically look and go, okay, well, I need to put enough space for my return value, at least in the system that I want to communicate to you, even though it's, hand wavy. We need to provide enough space for the arguments. The main function doesn't have any. We need to provide enough space for these variables in here. So we have an x, and we allocate some space for that, and we have a result. So we allocate some space. We don't know what values these have yet because we haven't actually processed our function, but we can allocate some space for them. Now, you will notice that the way that I laid this out is, and this is going to be a custom that I expect we're all going to follow when we do this. When we allocate a frame to the call stack, we'll put the return address at the top in the zero position, if you will. And then we're going to reverse order fill in, kind of like we go, if the last thing we do is we return something at this position and that's at the top, then the first variable will go on the bottom and we'll work our way up the call frame. This is not coming from nowhere. Generally speaking, what you will see is a similar pattern when you see memory entered in a call frame if you're actually looking down in the low level. However, the way that a real machine will decide to allocate memory inside a call frame is far more complicated than it's simply bottom up. It's going to do a lot of different things to try and save space and be able to do things more efficiently. And so it might break this ordering. However, generally speaking, this is what's going to happen. So the first thing we do is we allocate enough space for this function. We then get to our first statement here, and this is going to write x as 5 into the main frame. We see that the other positions, we still don't know what they are, but we've done a write. We understand that x is 5, which is why it's in red here. We step to our next statement, and now we see that we need to execute a call of foo. And so we don't know what the result of foo is yet until we've actually finished executing the body, over here. So what we do is we say, okay, I don't know what the answer to that is yet. I know that it's going to be enough space for an I32. So this will have reserved enough space for an I32, but we're going to wait. We're going to process first foo by adding another frame on. And so this one is for the function foo. And we're going to do the same process again. And when we're finished, whatever's in our return position here is going to update our result here. So we've allocated enough space. We've got enough space for the argument input here, which is also down the bottom. It's because it's the first thing we're going to do. We have enough space for y, and then we have enough space for our return. So we step in, and here, because the input in this context was 5 was passed to foo as an argument. 5 was, and that's why we had input 5 here. Sorry, we knew that when we brought it in, the input must have been 5. We can tell that y must be updated to 7, 5 plus 2. And then we know that 3 times that 7 is 21. And so our return position is 21. So now when we exit foo here, and so we pop the foo frame, we put back in our main frame, which is where we're returning to. We're coming back to this line now. We put the data of 21 back here. We're returning. This really has a arrow unit, like an empty set of brackets for it's returning nothing. It's an invisible return of the unit type, and so we just update the unit type is there. And after we finish, we pop our main frame. After you finish processing a function, you pop the frame, you get rid of that information, it's deallocated. And there you go, the stack's gone. It's all deallocated. So that whole process, once again, was we start with nothing, we get to main, we allocate enough space, we start updating the local variables. We get to the point where we have to do another function call of foo. And so we add another frame to process that call. We add the input in the concrete argument. We start stepping through, once again, updating the local variables of that frame till we get to the return position. We return the information back and pop off the frame, importantly. And then eventually we get to the end and we've popped that off. This is the what we can think of as the algorithm of how our memory inside our machine, when it sees these function calls, is working. And we can go down to the binary level and actually witness this. Yeah, last in, first out. That's it. Okay. How long do each of these classes for? They're going to go for a while. I'm going to try to go for, I mean, I'm obviously trying to go for 90 minutes because that's what I quoted you, but I'm probably going to end up going for like 2.5 hours, probably. Everything's recorded. Everyone is free to come and go as they please. It's all going to be happening, even if I'm the only one here doing it to the end, because you all come and go at different times. At least you're going to be able to go back and watch it later. So how function signatures are stored. The function signatures are going to be stored in the static memory. There will be information there. Oh, wait, sorry, you're making a claim that is very interesting, I think. Cool. Sorry, just in the interest of time, I'm going to be going quickly. Thanks for the kind words, everyone. Sweet, sweet, sweet. If a function don't have an explicit return type, how it's calculated the space for the return? Well, remember that this is not really what's going on. As I mentioned, this is hand wavy. Actually, return things are probably stored in register space on your CPU, but I want to teach about memory, and I want to be able to talk about return types. I don't want to have to go into the CPU architecture right now, well, at all. And so I'm just going to kind of borrow an idea and put this here. But the return types don't actually work like this, but we're going to consider that they do, just so that we can, in a nice sectioned environment, be able to work like this. Did you have a question? Did someone have a question there that they raised their hand for, or am I confused? Yeah, all Rust functions must have return types defined, except in a situation like this, this is going to assume, and well, it's going to assume that you want to put the return type as this type, the unit type, empty. Cool. Awesome. Nice. Okay, so now I should go back. And I should say, so I think that should be enough to understand what is going on with the stack. And actually, no, I'm not done. So what I want to say is, if we wanted to store something, let's say that foo here was going to store something like a vector, something that we could push data onto the end of in here. Or let's say that 5 was actually a vector, even more so. So 5 here, if it was something that we were able to push more data to, and it was going to take up more space here, our stack here in this situation, what would it need to do in order to account for if we passed a reference to 5 into foo, and then we started pushing more data onto 5? And so kind of we were trying to either overwrite this space by putting more and more data on there and growing the allocation and writing to it, or we obviously wouldn't want that to happen. That would be a catastrophe of a computer system to use. So if we were determined that we wanted to store a vector on the stack here and push that information down, what we would be forced to do is to try and update our bookkeeping and rewrite all of this information and push it down as we pushed the vector. That sounds like a really terrible experience for people to have to write. It's not that we couldn't write that. If we wanted our stack to work like that, we would be allowed to do it. But instead, what we say is, that sounds terrible. You're not allowed to put data that grows in size on the stack. It's just banned. Instead, what we're going to do is we're going to use a different region of memory, and we're going to add a pointer on the stack and say, hey, that growable region of memory, it starts over here. So let's have a look. With that as our motivation, the stack is wonderful. It allows us to deterministically process our call frames. However, it is not going to allow us to work with unsized data. We can only do it with fixed size data. So I encourage you to have a read of this. Like, here are some things I want to say, like what is the benefit of putting data on the stack? Would you not want to put data on the stack? And then another place where we could put information is on the heap. So the heap is typically accessed through the standard library. We don't have to do it that way. We can, I think if, as long as you're able to you would always have to go through at least the core library to get access to the heap. And I'll show you a bit more concretely what this looks like. But we think of things like this box and things like vectors. So this is this is like that type, like vector, like vec, like this. This would be a vec of I32s. So vectors like that, the payload in here, that is going to be stored in this heap, because we could add more values to the end here if we declared these as mutable, or we might want to be able to well, maybe not with the box. With the box, we're just saying that we're choosing that we want to put that on the heap for whatever reason. We do still store something on the stack by this saying let box and let vector. There is still information for each that is stored at the address where this is on the stack. And there it's going to have a pointer to point to this heap information to get to the payload of what's going on here. So let's have a look using the visualizer at what I mean by that. So
Daniel?
Yeah, go ahead.
Yeah, just regarding the last point you made for the stack. So when it comes to size data types, the compiler will basically look at a function and find all the size data types and kind of sum them all up to know how much space does this stack frame need to execute the function.
That's a simplified way of saying it, but yes, you can think of it that way. It's not that it's so much as going through and doing that. It's going to allocate like specific places to them, and it's going to need to offset them into certain positions depending on what the types are in particular. But you can think that it's summing them all up, and it does a little bit of extra magic to make sure that everything works fine, to put them all in nice aligned places. And so that it will allocate enough space to make sure that it has enough room for it by doing something similar to that.
Okay, thanks.
No problem. So going back over to here, we have the same program that I showed you before. And on the right-hand side, I'm showing a big amount of the unallocated stack and a big amount of the unallocated heap. And so before, I really wanted you to focus on the idea that this is like growing up and down. But really, all of this space actually exists in our virtual memory space. Like there is the virtual memory space that we were told you're allowed to work within this zone within this page. And those addresses are there. It's just that they're not storing any information. No one's got read or write permissions to them yet. And so what we want to do is, so I've listed them out like this now so that we can actually see that space is there already in some sense. And let's start stepping through. So of course, we initialize main, just like what Michael asked. So it's going to go through and calculate. And so when it sees a box, what does it need to calculate? So of course, I've got enough space for the return value there. And now we're going to need to go from here to here, bottom up. So boxed here, this type is a box that will store an I32. So what do we see on the stack at this position? What we see is boxed pointer and boxed metadata. What that's saying is this pointer, which it isn't populated yet, because right now all we're doing is reserving enough space. This pointer is going to point somewhere into this heap region, and we will eventually store there this number 5. And the metadata is if we are storing something and we don't already know just based on its type, this is an I32, so we know how many bytes that is. It's got a fixed type, but some things might have, we don't know how long they are. That's the whole point of that's one of the benefits of using the heap, is we could have unsized data that we're storing on there that we go, well, the type doesn't tell me how big this is. Instead, I need something extra to know how much data is stored there. And so I'm going to use this metadata field in that case to track how big it is. There are some other uses for when we need metadata, but for things like an I32 here, this will just be empty. We won't need to use it. A vector here, this is going to store that we see, in these 3 slots here. What we'll see under the hood is we're going to store a capacity, a length, and a pointer. So once again, this pointer is going to point somewhere in here. The capacity will be how much space we have allocated, and the length will be how much of that space we're actually using. I might take this opportunity to go and make that idea a bit more concrete before I actually step through this stuff. So here, I'll go into VS Code. And I'm going to make this bigger so you guys can see. Here is the same program, still the same one, guys. And let's have a look about what I'm talking about when I say that there's a box and like what are these regions that are stored. If we follow through to the box type, so this is showing me now where this is allocated or where this is defined inside the Rust compiler. And so we can follow tracing where it's going is it's going inside the standard library, inside the alloc module, inside source directory inside there, and inside box.rs, it is the type boxed. Of course, it provides us with some handy documentation saying that this is a pointer type and it's uniquely, Rust is about memory safety. So a lot of the time when we want a pointer, we don't just want a pointer, we want a unique pointer so that we don't have two competing things using the same space. It uniquely owns a pointer to a heap allocation. It tells us that this is going to be allocated on the heap. And it's generic, it's over some type T. So let's deconstruct down what this looks like. Notice that this is a struct box. However, the actual content we're storing inside these brackets here, inside these angle brackets, I might just get rid of all of that macro. That macro is only going to make things confusing. Inside these angle brackets, this is where we're dealing with the generics. And so this is a unique pointer to a type T. It told us that it's for an allocation of type T. So unique pointer to type T. And what we're adding for a bound on our generic here is this is okay to not be sized. It's fine if it is sized, but question mark sized says that it is allowed to be bigger. That's fine. The A here is interesting. This is the allocator. This, if we didn't have this documentation, this is what's going to give us the hint that, oh, this is going to start trying to store something on the heap. A is trait bounded to be an allocator, and we can hover over that and see that the allocator it's allowed to grow, shrink, data blocks. Is it going to say the heap in particular? It's going to allocate to the heap, and in particular, it is defaulted. This equals here on the type says that this has a default type of global. And so that's just going to default to whatever your system already uses. So if your operating system will have its default allocator, you are allowed to override it if you want to, but otherwise, and so generally we never do with just normal processes. Oh, I didn't even think about that stuff. It just does something. But that is what, so a box needs to know, okay, you want to give me a pointer and you want to give me an allocator. In my description here, I'm not going to assume that for granted. The unique pointer though here, if we follow that through, this is going to be all the way through, it ends up being a raw pointer. The raw pointer is a fat pointer and it has the actual pointer component plus this metadata component. We'll see more about this, but I'm just bringing this up for completeness now to show you what's going on. So that pointer is what I'm ultimately storing for the box here. And so that is both of these components. It's the actual address in memory and it's the metadata component. To do the same thing that I did just then, we'll make all of this just like it was in case I want to go back to it. To look at the same thing for a vector, inside a vector, if we go, what do we have? A vector is on type T. It also has an allocator that is defaulted to the global allocator. So we know straight away, okay, this is going to store something on the heap, but on the stack, because a struct is storing on the stack, what it's storing on the stack is a length and it's storing a buffer. So what is inside this buffer? If we go inside the buffer, don't worry about the phantom data. That ends up disappearing. That's why it's called phantom. But inside this raw vec inner, we have our unique pointer. So this is the pointer to the heap. So we're storing on the stack a pointer to the heap. Remember that if we go through, we see that this is actually just a raw pointer. But the raw vec inner is also storing a capacity. And so this capacity is how much that we've allocated. And the allocations are done once again through this allocator here onto the heap. If we want to get a more, how should I say, if we want to get a visual understanding of this, I encourage you to go up and look at the documentation here. The documentation, this in the context of what I'm showing, this information is on the heap. Oh, sorry, this information is on the stack. And so we have our, what did we see when I was over here? We had our pointer for the vector, our length for the vector, and our capacity for the vector. So on the stack, we're storing a pointer, a length, and a capacity. And that pointer is pointing to a heap allocation. So yes, that is going to be optimized out by the compiler, but I'm just trying to give you a complete understanding of how this stuff looks. So putting all that back, there's me showing you with the actual compiler what I'm abstracting away and showing you in this diagram. So let's step through and see how does this actually look. So first, everything's unallocated. Then we calculate how much space we need for these pointers and potential metadata and the length and the capacity that we're going to store in the stack. Right now, we don't have the payload stored anywhere. In fact, we don't even have this information stored. We've just reserved the space. We step in. Now we're executing the first statement, and that stores 5 somewhere on the stack. Let's say, oh, sorry, somewhere on the heap is storing the payload of this box, which is 5. Let's say that that's at the address 1234, OX1234. What's stored on the stack, because this boxed variable, this is our handle for how we access all of this data. So box needs to store the pointer to here, and because it's an I32, we already know how much space it's going to take up. It's not this unsized data thing. So we can just put unit for the memory side of things. And what I point out here is we didn't just go and do this. There wasn't like a deterministic way of doing this. Instead, we had to request to the allocator, hey, can you go and find me a place in memory and give me a virtual memory address where I'm allowed to start writing my data to, where you've allocated things for me. So, and to bring that back, that's what I was saying here about this allocator. This is talking to that MMU. So to bring back here, you can consider that it's going to this thing in the kernel, which is handling all of our virtual memory. And it's saying, okay, yeah, you can have one here. And I'll keep track of where all that is. So that allocator trait, where was I? That allocator trait, I'm in here. That's talking to that. So I'm trying to make the picture a bit more complete. Let's have a look at how that works. Where when we get to a vector, with a vector, we're storing 987 on the heap, but we're going to need to store information here on the stack to be able to do our bookkeeping and track, because we don't want to lose what's on the heap here. So vector, so now that we're executing this, the stack is a struct, it has pointer, length, capacity. So once again, we get a pointer. This time it's at OX2468. And so, and this is a convention that I want everyone to follow for when you're doing like the quiz questions or whatever. We're going to go from the bottom up. So 9 is going to be at the bottom here, and then we're rising up. And that actually makes sense if you think about it. It would be strange for it to be any other way. It doesn't make sense for it to be, because the vector pointer is pointing to here, and it would be the first element because it's the first part of the pointer. And then we have a length and a capacity. So when we first allocate this vector, we just want to have enough space for these 3 elements that are here. Those are what we're going to use. And so the capacity and the length are the same. We've allocated just enough space, and we're utilizing all of that space by writing those values to there. So the allocator spot at that location. Okay. I will just go through the deallocation part. So now when we get to the bottom here, we update, of course, the return. There's an invisible return type for the main function. And now that we get to the end here, we have to deallocate all of this stuff. And so last time when it was the stack, we just deleted it all out. We just kicked it all off and was like, cool, done. It's a little more complicated when we have pointers on here, which are pointing to heap allocations. Instead, what we see is when we're deallocating main, we have to call the destructor. First, we're going to do it on the vectors heap allocation. And so we go through, we follow this pointer and we say, there's a vector on the frame. It has a heap allocation. So we're going to go through and we're going to deallocate what's at that location. The box here is still on the frame and the box here is still allocated. This is still around. So after we've gone and we've got rid of that stuff on the heap, we then go and get rid of what's at the location here for the box. We're calling the destructor on the box. Now we've got rid of all of our heap stuff. We can do what we did when we were exiting it just on that stack diagram. Just everything gets unallocated. We finished. We can pop the mainframe. But while there's still heap stuff there, generally speaking, we're not going to leak it. And I say generally speaking because a memory leak Rust doesn't technically consider it a memory error. And under extremely specific circumstances, it will allow you to leak memory. But generally speaking, we go through and we clean all of this heap stuff off. Okay, I see that people have raised their hands. Do people have questions? I think Springfield, or maybe you were going to. Arthur, you look like you got a question.
It's not. So I know that there is like defining memory leak is something not straightforward.
Yeah.
But how would you consider what do you consider a memory leak on this case?
In this case, what I would consider a memory leak is if imagine. Oh, whoops. How am I confused? Here we go. I'm back. Imagine that instead of going through and removing this data here, imagine that we didn't deallocate it, so it's still allocated, and we then deallocated this stack data, and so now we have no pointer because we've just kicked this stuff off memory. We now have no pointer, no way of being able to trace back and find where this stuff is. So we can't go and deallocate it because we don't even know how to find it anymore. And so when our process ends, this is still going to be allocated memory. Now, admittedly, how dangerous that is depends on the scenario. If there's some sort of recursive process where a memory leak is going to continue doing this and you're going to end up running out of space in your memory, that's really not good. You don't want to be able to do that. However, if in a situation like this, where what we're going to do is we're just going to end the function, technically, whether or not this was deallocated or not, all of this provisioned memory for the entire process is going to get just destroyed immediately afterwards. So that's why it's like, does a memory leak matter? Yes, but also you need to be in specific circumstances where you can witness that being a problem. Cool.
Yeah, I have a question. Am I audible?
Go ahead. You're audible.
Yeah. So, for example, when we are allocating space for the box in the heap, there is a request that goes to the MMU requesting for virtual space where we can actually store all of that data. In that request, do we specify information about the kind of data we would like to store?
So do you mean, just to make sure that I understand your question first, are you talking about allocating space on the stack, or are you talking about allocating space on the heap like this?
In the heap.
And so I apologize, but could you ask your question again?
So my question was, when we make the request to the MMU to get that virtual space, do we specify information about the kind of data we would like to store? What I'm trying to ask here is there possibility for two calls to the MMU to return space in such a way that they can be overlap of the data stored?
No, it's not going to have any information about what is going to be stored at that location. It's purely going to change in this region of memory. What are the permissions? You can think of it as going, now you're allowed to write to this space. Previously, that was illegal. This is unallocated space. If I just try to do a write to it, that's not allowed. What it's going to say is we're going to go allocate some space to it. And I kind of like blend two steps together. Not only do we allocate some space and say you are allowed to write here, in this step, I also go and we did write to it. That is admittedly an oversimplification. There is a lot more that's going on actually under the hood when you're dealing with memory. But that I think is that's what we're going to talk about for today and maybe for the rest of the course, unless people are particularly interested in looking at the arenas. Does that answer your question?
Yeah, thanks.
Okay, no worries. Thank you for the question. Akoye, is that how I say your name?
Yeah, can you hear me?
Yes, I can hear you.
Yes, so my question is, yeah, nice explanations, by the way. I've been enjoying myself here.
Thank you. I'm glad to have you here.
Yeah, so what I kind of got confused at was when you're talking about the bottom-up kind of storage in a memory, on the stack rather. So I think you said something like for the vectors, right? Where we had the 9, the 8, the 7 on the heap, and then on the stack we had the pointer. So my own, because how I used to think about the memory is that the pointer points to like the first element, then when it wants to return it, it just copies like the length represents the bytes, so it just like copies from the pointer and copies the remaining bytes to like return. So now you said it's bottom up, so is it that it's now reversed? So it stores the pointer, like the pointer to the last, then it copies up. So that's like what I was trying to think about.
This is the first element, and in this it isn't written here, but we're considering that the high address is up. And so here, if this is a pointer to 2468, then that is pointing to 9 in this case. And then we want to copy 3 times the size of what's going on. And so if we have a look at what I have for this is defaulting to an I32. So I think I did my hex right here. So then this should be occupying, and I'm not considering padding or anything here, but this should be occupying 4 bytes. And so 4 bytes from here is we've got 9, 10, 11, 12. 12 in hex is C. And so we update this position to a C. And so we are doing what you said, where we're taking those bytes. But because our address space is going up, this is the high address, we move up that way. We are, this is the beginning point, and this is where we're writing up to. Does that make sense, or have I missed your point?
Yeah. No, you didn't miss the point. I just said like, can you go right again? So I just get it again.
Yeah, no worries. I'm happy to just to relay that one more time. So this address here, this pointer, we can consider that this pointer is pointing to the first element of this vector. So we know that the first element is 9. Yeah, that's our mental model of what is going on when we're storing these in a row. So if this is pointing to the first element, when we follow this pointer to 2468 and we go through, that's where we're expecting 9 to be. Now, we know that this is storing a contiguous block of elements at this point. So assuming that the length and the capacity are the same at this point, that we've allocated enough space and that we've actually used that space, these are both 3. And so we're storing 3 times the size of what the element is that's here. The element that's stored here, these are it's not obvious, I guess, but these are I32 integers because that's the default type for a number in Rust. So at this address, we store a 9. So this is an I32, so it's taking up 4 bytes of space because 1 byte is 8. And so 4 times 8 is So if we calculate 4 bytes, 4 bytes is enough space to store this 9. And so then going 4 bytes up, that's where we expect to find our next element that's stored here, this 8. And so that address going 4 bytes up is that 8 will change to a 9, and then it goes to a 10, then it goes to 11, and then it goes to 12. However, we just use A, B, C to store that. So this changes to a C. That's where 8 is stored. The same process is used to go to the third element. So C, D, E, F, and then we need to wrap around. F is the last one, and so we update the 6, and that goes to 0. We've used 4 bytes here to store 8, and then we will use 4 bytes here to store this. Did that cover it well enough?
Yeah, it does. Thank you.
Nice. Good question. I'm glad you asked that. Okay. I feel do I go ahead, Karim? You just cut the queue. Come in.
Yeah. I don't know. This might be a stupid question, but what would be stored in memory address 0x2469? Would that be binary representation of
it depends
9?
on the representation of the numbers, but what we could think of is if I go I'm going to type this out. Can you see this?
Yeah,
that's too small, isn't it? There we go. This will be big enough. So what we can think of is OX2468 is storing it's storing 9, but this type is an I32, right? So we can think of it like that. If I wish I had Vim here, but that's cool. I'm going to get over it. 9 as an I32, we can think of it like this. Remember that an I32, like I just explained, that's going to use 4 bytes. So we can think that if we consider that it's a little endian representation, which, you know, depending on architecture, it might not be, but the first 6, 7, 8, the first 8 bytes will be empty. Those are the high bytes. The next 8 bytes will be empty. The next 8 bytes, 1, 2, 3, 4, 5, 6, 7, 8. Oh, wait, did I get that right? Oops. I need one more. And then for 9, we're going to store, let me just start like this. And then for 9, we are going, it's odd, so we need a 1 there. And we're going to store like that. So this is like binary 9. So that's not really what's stored at OX28, right? We're storing 9 at OX28, but here I've just put in more stuff. So what we can think of is like what I had here. So if I go like that, and I go like this, here at C and here at 70, am I cooking this? Oh no, yeah, sorry. How am I describing this? So, oh no, yeah, that's what I was getting wrong. So this should have been 9. This should have been A, and so this should have been 6.
Yep.
And then yeah, that's where I was tripping myself up.
I think it's 9AB, wouldn't it be 9?
Yeah, like this, right? So here we're going to, but actually it's going to be like little endian. So we're going to do this, and so we can think of as we're doing that, right? And then really this part is deleted, and we're storing this part here. And does that make sense?
Cool. So it's just padding?
No, it's not that it's padding. Padding is something different. It is specifically 0 set information, because if we were to put a
Okay.
1 here, we would change the value of the number. It isn't
yeah.
that this is padding and it's just giving us some more space. This is holding the information of 0, and it is important that it holds the information of 0.
So, okay. Yep.
Yeah.
Yeah. Got it. This makes sense.
Nice. Good question. Oh, Michael, you're breaking up. I can tell you have a question though. Well, if it's an I-32, it's necessarily not padding a la Rundara, because an I-32, all of those bits are needed for information. Sorry, go ahead, Michael. Can you hear me? Or you're not audible, or maybe you're not intending to be audible, Michael. I don't know if that was intended. Michael, I can't. Oh yeah, maybe you weren't intending to. Yeah, all good. No worries. Okay, cool. I know that there's probably questions in the chat. I'm going to move on. We can get back to people's questions if they need them, but I feel like we also got to keep cognizant of keeping cooking. So we're going to go away from the heap, just at least for now. And we're going to talk about static memory, because this is the side of things that I haven't gone over yet, right? I've been talking about like, okay, we process the next function, we do the next thing, but I haven't even told you like where that information is, like how did we get there? So static memory is globally accessible memory for the entire program. So we can choose to store things in static memory. Like we could choose, this is not such a great example, I guess, because it's storing, but we could choose to say static number, and we could say, we need to give it a type. So let's explicitly say it's an I-32, and we'll say, you know, what 9999. That's our number. The location that this is stored when we say the static keyword is specifically going to be stored in static. Oh, sorry, sorry to point it out, but 9, wouldn't that be stored as? I might have screwed either the binary or the hex up. If I did that, I'm sorry, but I think the point that I was getting across was trying to be like, how is this laying out the information? Sorry if I screwed that stuff up. So this is being stored in static memory, and I'll go through a visualizer and I'll show where that belongs. Also true is all string literals. Like when we put something in strings like this, hello world, or hello universe in this case, this string literal itself is stored in static memory because we need to be able to read that from somewhere. We also here in this, we're storing as well in static memory a reference to it, which is like a pointer. So we're storing in static memory the address. Maybe that's not particularly clear, but there's two things here stored in static memory. There's the pointer to the string literal and the string literal itself. So both things are stored in static memory. And if I had have chosen to just do this and go let greeting stack be equal to hello whatever. So this is still of the type ampersand stir, right? So in this case, this is stored on the stack. It's stored in the frame of the main function, like I just showed you, greeting stack. However, this is a pointer to static memory where we're storing the string literal data. Okay, I feel like I will move on to the examples. So let's get into the visualizer. That's the best way to understand it. Well, I hope so. At least that's why I made it, is because I think it is. So what I point out here that is different. What I point out here that is different from where we've worked before is before, when we talked about our program starting, I started and there was nothing in the heap and there's nothing in the stack. Our program is read in the binary that we were storing in storage somewhere. We've decided, okay, let's read in this program into memory. We're going to start it. So before we've started looking at the main function, the thing to understand is we have already populated our static data. It is there for the lifetime of the program, and it is accessible from anywhere in the program. Any line inside the program is able to access the static data. It's there for the lifetime of the program and accessible for the lifetime of the program from anywhere. So something to think about when I say that that's when this stuff is populated is it is not the case that you should think about these as having their order or their position relative to their use, little asterisk, but I will be a bit more clear. But where they're called, where these lines are and where they're used doesn't matter. Notice here, I have the static greeting global. So this greeting global here is going to be a reference, which will have a pointer component to the string literal. So here on the stack, sorry, here in static memory, I have greeting global. There's the pointer, which is I've just given this value for it. And so it's pointing to another area in memory. And that area is here where we have hello universe. However, because this is just a stir, we don't know by the type itself, how long is this string going to go for? Is it going to go for, 5 characters, in which case we'll get this? Is it going to go for 10 characters, which will go to about there? Or is it going to go for 16 characters, which will give us all of this? Or could it go for, if we didn't try to figure out how long it was, we could start reading into other areas of data, and who knows what we'll read, and who knows, if we allow people to do that, what they'll be able to do with that access. So what we do when we have something where the type doesn't tell us how long this is going to be is, once again, just like we did for our raw pointer, just like we did for our box, we add metadata. So here I put it as length. You could say meta, or you could say length, but the semantics of it is it's storing the length. So here we also store 16. And so if we ever wanted to read from greeting global, we would follow the pointer. Okay, greeting global pointer, follow it to OX100, that's here. And then at how long am I reading for? And I look at the other component. Okay, here's my length. I'm reading for 16 characters. And so there, boom, and then you read it and you use it. That's what's going on there. So that information existing, it's used here in this print line, but it didn't need to happen before the use of print line. Notice that here I'm printing greeting, and greeting, the static line, comes after the print line. And so if you are used to thinking of, okay, when a program starts, it goes down like this, you might think, oh, well, this will create an error because we're using something prior to its declaration and definition. But because all statics are loaded at the time that we load our binary, it's already populated, and so this is a completely legal program. This won't error, and it makes sense that it doesn't error because of what region of memory we're storing this in. That is a point that I want to point out there. This greeting, hello world, it's the same logic here. The greeting has a pointer component. There it's storing, that pointer is storing, sorry, we're storing the pointer. If we follow that pointer, we read from that pointer, we get to hello world. how long do we need to read from? We need to look at the length component of the reference, and that is storing for 13, that will give us hello world. Okay, so let's go through. So before we've executed a line here, we're initializing main. So main, if you allow me to be hand wavy with the macros here, main doesn't have any allocation to any local variables. So we just have this return type or this return field. These functions, print lines are actually quite complicated. I'm happy to go into them with people maybe in the office hours, but just for now, just consider that I'm not joking when I say big oversimplification here, and that this is pretty rough calling it just this a function. But what we can think of is there's some sort of read that's happening here inside the format arg. Like there's a format arg here. We're providing greeting to it. And so we need to read from greeting. And so we're going to read from this 1DD, and that's this position here. And so we would then follow the logic that I laid out before. Same thing for greeting global. If we consider that we have this print line, we need to read from greeting global to put the information in the format arg there. So this format arg, we need to read from OX 150. That's here. And there's our pointer to the payload. Here's how long our payload is, the length. And so we can get the printing of hello universe and hello world that way. The same invisible return type. So we, once again, hand wavy, we deallocate that space for the print lines. Wow, I found an error, I guess, because that doesn't make sense. I don't know. Okay. All of this stuff, I guess it's not. This is very hand wavy. So let's just, that did change to unallocated, but these are quite complicated. We'll talk about them next week on Monday. But we do the return type here. And then when we deallocate, like we're popping this frame, all of this information is still there. This will get torn down when we actually destroy the entire Rust process. Okay, will greeting pointer be the bottom compared to greeting global pointer? With the way that I did it, that's how I did it. In reality, where things are stored in your binary is determined by the compression algorithm. And information like this, when it's trying to write to it and use the space in the most efficient way. So that is how I've laid things out, is in this way. It's then going to read from it. So like I said, the compression algorithm will decide how it's stored in the binary. And so then how the runtime decides it's going to peel that out, I actually don't even know what how it would decide where it's going to store things in that way. And then things are actually even further complicated. No, I won't talk about that. But then there are other complications that come along with it. There's a lot of obfuscation to try and stop people being able to like predict where addresses will be as well. And now, so with this information that we have here already, we understand that static information is populated at this time. So let's get some interaction. Straw poll. I'm going to make a poll. I'm going to pop it in the chat, and you guys are, I mean, if you would be so inclined, you're going to answer it. Create a poll. So what data can static data depend on? And it's going to be, there are answers. There's going to be static data, so it can refer to more static data. There's going to be stack data. And there's going to be heap data. Okay. So, yep, that makes sense. Creating the poll. And where are you guys? Okay, what does everyone think? And can I watch the answers come in live? I feel like I'm allowed. Show results. All right, we got Stack. Whoa, Static's coming in. All right, guys, I'm going to announce this live. Stack is absolutely taking it. Static is got a good showing. Some people believe that Heap is going to be involved. It's not out of the race just yet. We've got exactly one person who thinks the Heap, but Stack is taking it by storm. It's absolutely torn away. I don't know if Static and Heap are going to touch it at this point, but the votes are still coming in. We've got 66 people in the meeting, assuming that like 15% of them are AFK. We still got votes to come in. Stack is just absolutely tearing away. Look at the pie graph here. It is reducing though. Static is taking up some place. All right, the votes are slowing down. Not many people for Heap. Some people for Static, and the majority of people for Stack. Let's have a think about what it could be. So, if we think about the fact that this information has to be populated. If the stack and the heap meet, should we panic? If the stack and the heap meet, you're not going to be able to panic because you're going to have the runtime collapse because you will have overextended your stack bounds a mile. So it will handle the panic for you. You won't ever need to check that yourself. But maybe that's what you meant actually. But yeah, it'll shut down for you and say that you are writing to a region memory that you're not allowed. Yeah, where exactly that is, whether it's the operating system that's going to call that or whether that will be handled, where exactly that's handled, I'm not sure, Arthur. But okay, so going back to this other question, here we have already when we're provisioning when the memory is provisioned and we're loading in our binary, we already have the information before we reach the stack, and the stack is empty and the heap is empty here. We have already populated our static information. If we were to allow at this point for static information to depend on the stack, that would assume that we were able to read some information from an unallocated zone. So when the process first is happening like this, and if we have immutable static data, that data cannot rely on the stack, or it cannot read from the stack. It's not possible for us to get information from the stack. By the same reasoning, we can't get information from the heap. If our program then continues, and I said that some statics can be mutable. So if we had the mute keyword here, we would be able to read data in from the stack and update our static memory with that data. However, we would not be allowed to provide a reference to it. So we wouldn't be allowed to store a pointer here that pointed to the stack, because what would happen is we would get to the end of our program and this information would be unallocated. And here we would still have a pointer that we could theoretically read from to that unallocated area. So when I said and that same reasoning goes for the heap. So when I said depend on, I probably should have been at least a little bit more precise. I sort of cooked the question up in my head as I did it. But we can't have a pointer stored here or any reference to these regions of memory. We can internally refer to between static memory because that lives for the entirety of the program. And if we have mutable static data, we can update our writes, and we often would update our writes dependent on the manipulations that we had from either stack data or heap data. So that's the result of that. So there's my explanation. It's not that these are necessarily wrong. It might depend on what I mean by depend on.
Daniel, I have a question about that.
Yeah.
Specifically, like you could have static attribute, like a static variable in a function.
Yeah.
Right. That shows up on the stack, right? Or is it?
So, no. These are stored in static memory. There is no handle that's stored on the stack for greeting or for greeting global. If I understand things correctly, which I feel like I did look at a lot of binary when I wrote all this.
No. I'm just trying to conceptualize what static means when you're defining it in a function. Like,
well, okay, actually think about it. So, not that you weren't, but let's think about it in a different way. So as I mentioned all the way back up here, if I scroll for a while, we're also storing in static memory our text segment and our code segment. So when we are executing through functions like this, there is also, not that I'm showing it here, but there's also in static memory the actual binary, and we have some pointer stored in our register, our program counter, right?
got it.
That is storing where we go to. And so when it gets a reference to go to somewhere, it will for greeting and greeting global, it will refer into this space. It won't ever be, it doesn't need to touch stack information. Does that make sense?
Yeah. Okay. That clarifies it. Thanks.
Nice. Yeah. Naruman, I don't know if I got the name right, but yeah.
Yeah. That's good. Nice. Thanks for the awesome explanation. That's really that's really good. I mean,
Yeah,
I'm really
glad you like
really feeling it. Just a quickie, because I never reversed the string for the Rust, and as we know, they are like a Unicode native. So when we're storing, like when you showed it, even for the statics, when we store it, do we have any kind of when it's ASCII, it's pretty simple. We just store like numbers, and they're ASCII because of the type. They'll just So how does Rust handle the Unicode stuff? Do we need extra storage for that, or it's something on the compiler side?
Well, it depends whether you write your logic of your program to depend on assuming that a character is going to be 1 byte. As we know, with UTF-8 and Unicode characters, they can extend beyond that. So if you use the Rust paradigms and utilities that they give you, they should already be handling the Unicode information. If you just take in, say, from standard in a raw stream of bytes, and you decide I'm going to interpret this as chars, like that's when you start to get into, okay, well, how are we going to determine how we're going to do this sort of thing? And that is complicated, but there are standard ways of doing things with the standard library. Are they going to cover every case perfectly if you're dealing with a stream of data? I don't know in particular, but there are complications there. However, at the same time, when we're talking about something like this, where we're putting in here and we're clearly encoding particular chars, this we may have a char that is more than 1 bytes extending here, and I'm not considering that as not part of the model that I have here. But does that answer your question?
Yeah, so we don't store actually nothing extra. It's all like on the compiler side or the toolchain side, and so because Unicode by default, so in say 01, number 5, we're the OX 0100. We're just storing the larger chunk of the data compared to the ASCII ones, which would be like proof of C.
In a situation like this is absolutely going to be handled entirely by the compiler. But you could also theoretically write a program to say, go to, man, I should have added a text box here so that I could type at the same time right in this location. But did I keep the other one around? Yeah, but let's say that I decided that I was going to write a program and I was going to go for, oh no, yeah, how should I say this? Let's go, yeah, maybe this is going to be pseudo Rust for
like handling like a binary formats like fixed protocol when you get like stream of data and you just bit them in the bytes and process each of them. So you have to take in account that they are like what format they are coming from, right?
Yeah. So let's say that I was going to do something like this. Let's say I was going to do something like that. This logic in my program is assuming something, right? It's assuming that at these boundaries like this, actually, even if I was to do something like this, I wonder if, because it knows that the type of greeting is a stir, even this might actually handle it. However, if I were to do a casting, if I were to cast this, let's say greeting as, let's just say bytes, this is like pseudocode. And then I was to do something like this, and I was to say like I as char. I think then I've really cooked myself. Yeah.
No. Yeah, it definitely it is. Thanks a lot. That's really insightful because like I mean, it's going pretty deep into the one of the like most challenging stuff in the Rust is actually the strings, which mostly unexpected, but they're challenging. So thanks a lot.
Yeah, no problem. I love the question. Thank you. Okay, cool. So, talking once again about what I was saying to do with, hold your horses. I'm just going to go for a walk. So what I was talking about with the data. So in a situation like this, if I was to try and declare numbers as my vector of numbers, it's going to say, I can't do that. We're at the static memory portion of, or provisioning the static memory side of things. I can't rely on heap data. I can't even talk about the heap yet. None of that stuff is around. And at the same time, if I was to say, let immutable number I32 equal 55, and then I go, okay, cool. So in the next line, I'm going to assign into number in static memory that immutable number. Well, as we just saw, this doesn't make any sense because I'm assuming that these statements are executed one after the other, but actually this is happening before we even have a main frame on the stack, before we even have the main frame. So we certainly don't have an immutable number 55. And if you try to do this, it certainly will error. Cool. So, and I did mention, and I feel like I should add a section for this. So let me write a note because I would like to do that. Do I have a section for notes in here? Notes. Oh, to do. Fix me. That's what I'll do. Fix me. Add to static data section text segment. I want to talk about the instructions there because Amal's misunderstanding that he had is really understandable, and I think that it makes a lot more sense if you think that the instructions are also there, and that's where all of our like actual function signatures and stuff like that are. And so if we just think of things as being stacked first, that doesn't then this model would indeed be confusing. All right, let's jump into that's the end here. So I guess before I go on further, and I know that I've taken up a lot of time, there is a bunch of other stuff that I want people to look at. The last one here, statics example with commands to inspect binary. This is something that I wrote, and what I wanted to offer you is there's just I guess a bit of a clunky program here, but it's got like constants, statics, different kinds of statics, and we should expect these to be in different sections of the binary, and thus in different sections of static memory. And so what I mean is like different things would be stored here, or if they're stored within the data segment, they might be stored in a mutable section of the data section or a read-only section of the data section. And then there's also the BSS, the block started by symbol. So some people, and the thing is, this stuff exists in the binary, and then we load it into static memory. And so one nice exercise or thing to do if people want more, because you should always have enough information to do stuff if you're interested, is you can go through that program, and on a general Linux operating system, if you follow these steps and you just play around and you know you're curious, you'll be able to inspect in this ELF file and dump out the different sections like the data block started by symbol read only data, and you can have a look, and it should show you a view that is rendering things like string data, and then there'll be things which aren't. Like you will be able to go in and find every error message that your Rust program could possibly generate, every string literal that your Rust program has, and you know, all of these sorts of things. You could go through and you know, that might be fun for some people. Some people like or might be interested in doing binary analysis. It's pretty naive at that stage. You're just looking at different sections of a binary, not of a running program.
Daniel, on that topic,
Hmm?
is it possible for a compiler setting where it would inline a string within a function? Because a string is just bytes, right? Is there a situation where that happens?
Not if you're using the type here. At the type level, where are
Oh,
we?
it gets sorted by type. Okay.
Yeah, at the type here, this will not be able to do that. However, that doesn't stop you. Like if we look at, let's go Rust docs string. So string in the standard library does not work like that. Instead, if we follow through to the source code here and we have a look, a string is actually a vector of bytes, UA.
Right.
And so that is where it's interpreting that. And as well for what you said, Nariman, there's going to be logic here in order to interpret like how many of these do we need for a character. Yeah. Yeah, so that idea does exist. Sorry, go ahead.
If we want to inspect for all strings that could be emitted from a Rust code, we would have to look for these too.
Yes, yeah. And also, that is necessarily a runtime question. Right?
Yes. Okay.
Because this is a vector. So this doesn't exist at the time of static
Dynamic,
compilation.
yep.
Yes,
Yep,
dynamic.
yep.
Nice. But yes, so when I say all possible strings before, maybe I should have said all possible stir. Yeah, like it's not actually the strings. Yeah, okay. So there's a couple of other things. I think that 2 hours or just over 2 hours is probably good enough for the first one. I know there's a lot of stuff here for people to take in. I would love to go through some of this actual code a bit more. Maybe on the office hours, we can dig into going through a debugger and actually looking at these sections of memory as they are, where we actually interrupt the process of a running program. I can also, I could also go through these commands here and show you me. And by the way, this stuff, this is going to come back. we're going to do the same thing again for an SBPF program. It's going to like this. This is not like, this doesn't make any sense for Solana, but like the fact that we can do all this stuff now just on generic Rust code, but then in the end we can also go and we can get an SBPF binary, and we will need modified instructions that are provided to us from the Solana toolkit, but they will still be called object dump, and we will still need read elf and all these things, because a Solana program is an elf file. That is what is actually stored on chain. So it isn't that this is just like esoteric whatever. You know, you can look at this stuff, and people do look at this stuff when trying to analyze Solana programs. All right, so should we call it a wrap there? I think that that's great for the first one. Thank you very much for all the questions and engagement, and also looking at the number of people who have stayed around, also your persistence. I know that went for quite a while. I really do enjoy the engagement. Yeah, thank you. Are you still around, Lucas? Maybe not. He might have had some other stuff on, but yeah, okay. Thank you, everyone. Feel free to ask questions in the Slack. I encourage you to use a public channel for it so that everyone can benefit from the questions. I will be checking it periodically. I do also have a job, so I can't like just be there all the time, but like I will try to get to it. Okay, Lucas is there, guys, but his mic's not working, but I'm sure that he sends his thanks to everyone for sticking around. All right. Have a good rest of your week, and I'll see you in a couple of days. Oh, there you
Thank
are.
you. Thanks a lot. Have a good day, everybody.
See you, everyone.
Bye.